Hello, I'm Dr. Ziad Tahir. This video tutorial is solution to problem 12 of chapter 4 from Engineering Mechanics Static, ninth edition by J.L. Meriam, L.J. Craig, and J.N. Bolton. Statement of the problem is a drawbridge is being raised by a cable EI. So that is a bridge raised by cable EI. The four joint loading shown result from the weight of roadway. So these four joint loading 2 kilopound force, 4 kilopound force, again 4 kilopound and 2 kilopound. So they show the weight of the roadway. Determine the forces in member EF, DE, DF, CD, and FG. So need to find member forces EF, DE, DE, DF, CD, and then FG. So this problem can be solved using first passing a section there and then solving joint, and I'm going to solve it using method of joint. So these are steps to find member forces using method of joint. The first need to select a joint with at least one known force and two or less than two unknown member forces or reaction. So four loads are applied at A, B, C, and D. At joint D, it is connected with three members. So there are three member forces. At joint C, it is connected with four members. Joint B also connected with four members, and joint A is connected with two members. But A is a pin support, so it will have two reactions. So no joint satisfy this condition, so need to find support reaction first. These are steps to find reactions in a truss. So need to draw a free body diagram of entire truss by ignoring internal member, replacing support with reaction. So A is a pin support, so it will have two reactions, and then need to apply conditions of equilibrium, and you can choose any direction for the reaction. The free body diagram of truss is drawn here. So two sports reaction AX and AY are represented, and then tension in EIT is being represented. So tension is always away from the joint, so it is assumed towards away from the joint. And then uh, in this problem, because most of the sides are along the length of bridge and height of bridge, and loads are vertical, I am going to assume reference axis, x-axis along length of the bridge and y-axis along height of the bridge. So in this way, uh, I don't have to find component of these members A, B, B, C, C, D lengths along global x or y. So in this problem, the reference axis once again is taken along length of the bridge and then along height of the bridge. So that's why the reaction AX is taken along x prime x axis, and AY is taken as A about y prime axis. Now to apply conditions of equilibrium, it is necessary to resolve these given loads along y-axis and then tension along x-axis and y-axis. So now if I just consider here a triangle ABB dash, so in that triangle angle BAB dash is 20, so that's angle perpendicular at B dash. So then angle ABB dash is 70, and then I have drawn a reference line parallel to BG. So then angle of load with new y-axis or y dash axis is 20 degree. So similarly, all the loads are resolved into their components about y dash So the load 2, its component about y dash is 2 cos 20. And then t is resolved into two components, ty dash and tx dash. Now, because if I find tension in the wire EI, so then I can start with joint E. If I take moment about point A, so by taking moment about point A, so I can eliminate AX dash and AY dash, and then I can find these components only. So I am going to apply sigma m about point A equal to 0 using x dash axis and y dash axis. So now taking moment about point A and considering components of load, so along length of the bridge 4 cos 20 is going to produce moment in anticlockwise direction. Other 4 cos 20 acting at C is going to produce anticlockwise, and 2 cos 20 is going to produce moment in anticlockwise direction. Then Tx, that's the line of action of Tx along DE, and the perpendicular distance from line of action to point A is AD, which is 30, and Ty is going to produce moment in anticlockwise direction. And similarly, the line of action of Tx dash is along HE, that is the line of action, and the perpendicular distance is HA. So Tx is going to produce moment in anticlockwise direction. So moment due to Tx dash is anticlockwise, moment due to Ty dash is anticlockwise, whereas moment due to 4 cos 20, 4 cos 20 and 2 cos 20 at B, C and D respectively, they are clockwise. So I can apply sigma m equal to 0. So Ty dash times by 30 plus Tx dash times by AH equal to 8, and then minus 4 cos 20 times AB, which is 10 feet, then 4 cos 20 at C times by 20 feet, and then 2 cos 20 times by AB 30 feet. And then after simplifying it, the angle of I with horizontal axis is 50. So Ty is T sine 50 times by 30, and Tx prime is T cos 50 times by 8, and it is equal to 180 cos 20, and then T, that is 6.0143 kilopounds. Because the answer is positive, so it means that assumed direction of tension is correct. So now tension along EI cable is calculated. So now I can start with joint E. Now joint E, that satisfy the condition because it has two unknown member forces. So then I need to isolate the joint, draw its free body diagram by assuming all unknown member forces in tension, arrows away from the joint, and then need to apply conditions of equilibrium by resolving inclined member into their components. So that's the free body diagram of joint E. So EF and DE assumed in tension, so they are acting along x prime axis and y prime axis, and T is an inclined member, so need to resolve T into its component along x prime. And so at joint E, inclined member T is resolved into its components along y dash and x dash, and then there are one unknown in vertical direction and one unknown in horizontal direction. So I can either go for sigma fx equal to 0 or sigma fy equal to 0. So applying sigma fy dash equal to 0, so dE is negative and ty dash is positive. So minus dE plus ty is equal to 0. So dE is equal to t sine 50, angle of T with horizontal is 50. So then T already calculated as 6.013 kilopounds. So by substituting the value here, so it is 6.0143 sine 50. So DE is 4.60. Next, applying sigma f x dash equal to 0. So both EF and TX are towards negative x dash axis. So both are taken as negative. Minus EX minus TX dash is equal to 0. So EX is minus TX dash, and then it is minus T cos 50. So by substituting the value of T, EF is minus 3.8659. So now interpretation of the sign. So because initially all members, they were assumed in tension, so interpretation of sign is a positive value indicate tension and a negative value indicate compression. So DE is positive, so DE is in tension, and EF is negative, so DE is in compression. So that is the solution for member forces at joint D. DE is 4.6072 kilopounds in tension, and EF is 3.8659 kilopounds in compression. So step 4 is to repeat step 1 to step 3 for adjacent joint that have now 2 or less than 2 unknown. So after solving joint E, the adjacent joints are F and D. So at joint D, there are 2 unknowns, and joint F, there are 3 unknowns. So I'm going to solve now joint D. So free body diagram of joint D is drawn. At joint D, DE is known now, and then 20 kilopound force is also known, making an angle 20 with y-axis, and then CD and DF both are assumed in tension. So now DF is an inclined member. So DF is an inclined member, and the direction of DF is along length of the bridge is FDC. So angle of FD and along length of the bridge CD, so it can be calculated using triangle CFD, and in the triangle its side CD is 10 and its side FC is 8. So I'm going to use triangle to resolve DF into its components. So inclined members at joint D are resolved into their components along x dash axis and y dash axis. So load 2 is resolved in 2 cos 20, and other component is 2 sin 20. And similarly DF as DF y dash and then DF x dash. So now there is one unknown in vertical direction and 2 unknown in horizontal direction. So I'm going to apply sigma Fy equal to 0 first. So sigma Fy dash is equal to 0. So one is dFy dash, the other one is dE, and the third one is 2 cos 20. So both of these two first are positive and 2 cos 20 is negative. So then writing that dFy dash plus dE minus 2 cos 20 is equal to 0. So dFy dash is equal to minus dE plus 2 cos 20. So dE is already calculated as 4.6072. So by substituting the value of dE and then dFy dash, that is a y component, and I'm going to use triangles to find the component. So if in a triangle, horizontal distance, horizontal side is x, vertical side is y, and diagonal is z, so then Fy is force times by y side of a triangle divided by the diagonal or hypotenuse. So here dF times y side of the triangle divided by the hypotenuse, so that is 8/164, and then after simplifying it, dF is minus 4.3666 kilopounds. So once DF is calculated, so then I'm going to apply sigma F x dash equal to 0. Now applying sigma F dash x equal to 0, so CD is negative, DFX dash is negative, and then there is component of load 2 sine 20, which is also negative. So CD is minus DFX dash minus 2 sine 20. So DF is already calculated, and then horizontal component DFX dash. So using sides of a triangle, so horizontal component is force times by horizontal side over diagonal or hypotenuse. So to find CDF dash, it's DFX dash. So it is DF times by the horizontal side 10 divided by the hypotenuse root 164. And then after substituting the value of DF and simplifying it, the answer CD is plus 2.7257. So again, the interpretation of the sign, a positive value indicate tension and a negative value indicate compression. So DF is negative, so is compression, and CD is positive, so that member force is in tension. So joint member forces at joint DF is 4.3 kilopounds in compression and CD is 2.7 kilopounds tension. So now after solving joint D, then adjacent joint is C and F. At C, there are three unknowns, so it is not possible to solve joint C at the moment. And then I'm going to solve joint F because the forces FG is the only force which is left because CF is not required. So I'm going to draw a free body diagram of joint F now. So that's free body diagram of joint F. At joint F, FG and CF are unknown, and then EF and DF are already calculated. Then FG, EF, they are along X dash axis. CF is along Y dash axis. So DF is inclined member. So again, that DF, its components are calculated using triangle FCD. So that triangle is drawn there to find components of DF. Now at joint F, DF is resolved into its components. So one is DFX and the other one is DFY. So at joint only FG is required. So I'm going to apply sigma Fx dash equal to 0. So along X dash axis, so DFX is negative and FG is negative. And the other one is EF, that is also negative. So now applying sigma Fx dash equal to 0. So minus FG minus EF minus DFX dash. FG is minus EF minus DFX dash. So EF is already given, known, and DFX is calculated using force times by the horizontal side of the triangle divided by hypotenuse. So that is DF times 10 over root 164. And then solving, FG is minus 7.2756. Now a negative value indicate compression. So FG is in compression. So that is a solution of FG, 7.27 kilopound force compression from joint F. So now the answers in the book are EF as 3.87 compression. So EF is 3.87 compression. Then DE is 4.61 tension. DE is 4.61 after rounding, that is tension. Then DF is 4.37 compression. DF is 4.37 compression. CD is 2.73 tension. So that is 2.73 tension. And finally, FG is 7.28 compression and FG is 7.28 compression. After rounding all those, because I have used five significant figures or four up to four decimal places. So after rounding all the answers, so they matches with the book. So thank you very much for watching.